Let's take a look now at section 8.7, and let's talk about integration by tables. The name is a little misleading. It makes it sound like we're going to have some tables that we're going to be using to integrate the same way we had table that we use for integration by parts. It looks like we're going to set up a table and use that to organize our information. That's not exactly what we mean here. We've seen integration techniques starting from Cal 1. We've seen the power rule for integration. We've seen the integrals of trig functions. We've seen the integrals that involve logarithms and exponentials, the arc function, the hyperbolic and inverse hyperbolic functions. And in this chapter, we've seen things about partial fractions. We've seen things about trigonometric integrals and trigonometric substitutions. And we've seen integration by parts as well. All of those things give us a wide variety of options. We have the option to try one particular integral or another. Now the problem is, which one should I try? The other problem is, maybe I don't remember all of them. Maybe I think I remember one and I have a negative in the wrong place, and all of a sudden it's not valid anymore. So in this section, we're going to be looking at what are called integration tables, which is really just a more formal way of saying, let's take a look at our notes. Let's take a look at what we've written down from Cal 1 and Cal 2 and use that to organize our thoughts to help us integrate. So in this section, we're not going to be seeing any new integration techniques. Rather, we're going to be seeing how, once you have a variety of integration techniques, integration becomes more a matter of pattern recognition and being able to use these different techniques with the pattern that we establish, that we notice. So let's begin by taking a look at what an integration table looks like. This is an integration table from the back of our current textbook. You'll notice up here I have Calculus 11th edition. And this is just an electronic copy of our current textbook. If we have If you look at the back of your textbook, you should have one, whether you have the electronic copy or the physical copy. It's way in the back on, it's in the appendix section. So the appendix will be at the very end after chapter 13. You'll have appendices, and appendix number 2 is an integration table. All right, so what an integration table is nothing more than, basically your notes. These are very good notes, very thorough notes, where they've written down every integration result that you have seen throughout Cal 1 and Cal 2. I don't believe there's any here that you wouldn't already have seen. There's nothing here from Cal 3, essentially. So the two things to notice about these integration tables. One is, it's a bunch of formulas. That's great, right? Because I can just plug things in. But the other thing to notice is how many formulas there are. Here, I notice I have, if I go to the bottom, it looks like I have 100 different formulas. And, well, if I have one problem, which of these 100 is the correct one? Well, I don't know. It depends on what my problem is. The other thing to note is a lot of these formulas are very similar to each other. For example, here, the difference between this one and this one is, let's see. This one has a numerator of constant. This one's got a numerator that's a variable. And between those two, you have a very substantially different looking answer. Same thing over here. The difference between this one and this one is a single variable here. But, there's a bit of a difference between those. If you look up here, again, notice they're all just very slight variations on each other. But even those slight variations give you sometimes radically different looking results. So, yes, these are formulas, which is nice because you can plug things in. Unfortunately, this is not exactly the end of the story. It's not like, okay, I have this table, that means I can now integrate anything and everything in the world. Rather, it means we have a collection of options that we can now work with. The question is, how do I know which one works? Once you have enough integration techniques, and I've alluded to this in the past, a big part of integration has to do with pattern recognition and using the right substitution, whether it be a trigonometric substitution, a U substitution, or a few others which we don't really cover in this class. an appropriate substitution will take you from whatever problem you have to something that may appear on this current list. So let's take a look at this in action. You'll note that in this section we don't have any new theorems, new techniques, or new definitions. Rather, we're going to be just jumping in directly to see examples. And when we look at the examples, we're going to compare those to what we have here. So coming back to our problems, let's take an example. So let's begin by asking, as an example, what is the integral of e to the 3x over e to the 6x plus 9 dx. Okay, this looks pretty straightforward. I have an exponential function, so I should just have some formula in my formula sheet, in my integration table, that tells me how to handle that exponential function. So switching back to the other page, here we just look for some exponential functions. Okay, so scrolling down, these are all, here it's even organized nicely by giving you the form of the expression. So here these are powers, here this is the, here's where you have a linear expression, here's where you have quadratic expressions and square roots and so forth. So scrolling down, we'll look for exponential functions. We have trigonometric functions, and here we go, here are the exponential functions that I see. Okay, so I have 1 over 1 plus e to the u. Well, unfortunately, I don't have anything quite like that, do I? My problem looks like this. I have an exponential on top and an exponential plus a constant on the bottom. These aren't even the same exponential, but whatever. E to a power over e to a power plus a constant. But none of those look quite like that. This one comes pretty close, but it's not really correct. Well, see, you can't really expect for it to look just like this, because in these integration tables, what we have is the most simplified form of each category of function. Here, this is the most simplified form. However, this u could be many different things. This u could be an x, or it could be the sine of x, or the cosine of x, or a quadratic, or a cubic, or really many, many other things. Here, this assumes that you already have done the substitution that is required for the integration. So that means that chances are, if you're just given an arbitrary function, you're not just going to find it on one of these tables. Rather, you're going to have to perform some substitutions, and then, assuming the substitutions are valid, you then can go back and see if we can't find that result. So let's take a look. Here, well, I notice I have e to a power. It's a different power, but, well, maybe I should use that as my substitution. Okay, well, I have this one and this one. Okay, so which one should I use? Or maybe I should use the entire denominator. Okay, well, here, let's give a try to the entire denominator. Let's say that's my choice of u. Okay, well then du is going to be the derivative of e to the 6x is, again, e to the 6x. But now, because of the chain rule, that's going to be the derivative of 6x gets multiplied in, and then the derivative of 9 is a constant, the derivative of a constant is a 0. So that would be dx. And unfortunately, that just doesn't look right, because my exponent is still wrong. Sure, I could go ahead and make that 6 go away by dividing both sides by 6, but here, that power is wrong. Okay, so that may not be the right substitution. Now, maybe it is. Maybe I can reconcile. Maybe I can find some way to fix this. But it doesn't really look right. It doesn't look like that's going to match up. So that may not be the right choice of substitution. Okay, well, that entire expression was not correct as my substitution. I could just choose e to the 6x without the 9, but I would have the same problem. After all, the derivative of 9 was 0, so having that there or not doesn't really make much of a difference. So maybe let me try this as my substitution. Let's try e to the 3x. And again, there's no guarantee that's going to work, but it's worth a try. Okay, so e to the 3x, then du is going to be e to the 3x again, but now we have a times 3 because of the chain rule, dx. Okay, well now that works. I have, well, let's see. e to the 3x is that one right there, so I could call that u. No, but that doesn't work because I need that e to the 3x dx together so that I can have a differential. Okay, so here, I don't want to call that u. I want to keep that together with my differential and call that du. Well, okay, let's divide both sides by 3. I want to call it 1/3 du. So be mindful of that. Here, just because that was my substitution doesn't mean it's going to be u, because here I need to keep this together to form my differential. So here that's going to be the integral of e to the 3x dx. If I don't have that, then I can't form my differential. So I need to keep those together. So that's going to be 1/3 du, 1/3 du over. Okay, well now here my power is still wrong. Well, yeah, but if I square this, I get this. If I square both sides, that's e to the 3x squared, which here these two would get multiplied together, and that will give me e to the 6x. So here that's going to be u squared. Here's my e to the 6x plus 9. And here I can write that as the integral of, let me pull that 1/3 out. After all, it's a constant factor. Let me just pull that out, factor it out. Du over u squared plus 9. Okay. Now, you might recognize this if you think back to chapter 5, but if you don't, again, that's the point of our table. So let's go back and look for our table. What we're looking for is something with a quadratic, the sum of u squared plus 9 in the denominator. That 1/3, we don't really worry about that. We're looking for a quadratic in the denominator. So over here, let's see, I need a quadratic. So these are, that's just the power rule. Here, these are linear. Here, these are quadratic, but they're not the right kind of quadratic. Right here, this is a quadratic where I have a linear term, and I don't have that in my problem. My problem is just quadratic plus constant. Okay, so let's keep going. It's none of those. Let's see. Here we go. Quadratic where you have a variable plus a constant. In fact, that's this one right here. I have variable squared plus constant squared. So, let's see. I have that one there, which, let's see, can I blow that up any further? Yes, I have that right there. Right there. I end up with 1 over a squared plus u squared, which is what I have. I have 1 over, there's my a squared plus my u squared. So I have that a is equal to 3, because that's what's squared to give me 9. And u is, well, it's just u. It looks exactly the same. Here, so I'm going to write the u equals u, which is technically true. Yeah? And so here, using this form, I have 1 over a, arctangent of u over a, plus a constant of integration. Don't forget that extra 1/3 is just multiplied in. So that's going to be 1 over a times the arctangent of u over a, plus my constant of integration. And finally, we can take that u that we substituted in and back substitute. So this will give us 1 over 9, multiply these together, the arctangent of e to the 3x over 3. Plus our constant of integration. Just like that. All right, so let's take a look at another example. Let's say what we're looking for is the integral of the natural log of x over x times the square root of 2 plus 3 natural log of x dx, like that. Again, it's unlikely you're going to go to your integral table and find anything that looks like that or even remotely close to that without a substitution. Sometimes, if the integral is simple enough, it might look just like something on the table. But chances are, if it looks just like something on the table, it's probably simple enough you could do it without the table. It's probably simple enough you could do it using what we learned in Cal 1. So here, let's go back to our table and see what we can find. And, maybe we'll get lucky and we'll see something that looks exactly like that. All right, so let's see. I'm looking for a natural logarithm divided by the square root of a natural logarithm. Okay, so yeah, nothing like that. I don't see anything remotely close to that. Here are the only integrals that involve natural logarithms, and none of them are a natural log over the square root of another natural log. Okay, so apparently that's not the right substitution. That's not the right thing to be looking at. We don't want to be looking in terms of natural log. What we want to do is we want to see if we can find a valid substitution. So coming back over here, I look at a more generic pattern. I have a function over a variable, square root of that function. Okay, so let's see if we can find something that looks like that. Function over variable, square root of function. Okay. Well, we need something that involves a square root in a denominator. So obviously none of these are going to work. Starting from here. Here I have some square roots in my denominator. Let's see. I have a square root here, but I should have that function not just down here in the radical, but it should also be in the numerator as well. Okay, so that's not right. Neither is that one. Here, that's in the numerator. I want my radical in my denominator. That's pretty close, though. If these were upside down, that would look about right. This one looks pretty good. I have a variable, I have a function up here over the square root of that function as well. However, I notice that I don't have a variable out here, which in my problem, I have this extra x variable. So maybe that's close enough. Maybe we'll be able to make that x go away through the substitution, or maybe we're wrong, and maybe that's not the correct integral. So let's go ahead and give that a try. It looks fairly close. I have a function on top, square root of constant plus function on the bottom. I have a function on top and square root of constant plus function on the bottom. Here I don't have a power in the numerator, so it shouldn't be number 22. Let's try number 21. Let's see what happens. From this substitution, it looks like I want u to be the natural log of x. So let's give that a try. Again, the worst that can happen is that we're wrong, and well, we'll try something else. So just like up here, we're going to find our substitution, and maybe we're wrong, but we'll give it a try. U is equal to the natural log of x. So that means du is going to be 1 over x dx. So that's what's going to force that x to be there. Okay, so that does look like it's going to work. So this would be the integral of, we're calling that u over this dx over that x, that dx over that x, that's just du. All right, that x hasn't gone anywhere. Rather, together with this dx, that forms our du, or differential in terms of u. And now in our denominator, we have square root of 2 plus 3u. 2 plus 3u. Okay, so now going back to our, let's see here. Yeah, this one. Going back to our result here, I'm looking at number 21, and it looks like this one here. I want the integral of u over a plus bu du to equal to all that stuff there. Okay, well, let's see what I have. I have my a is just that number 2 by itself. So a is equal to 2. And here b is equal to 3. That's the coefficient on this u. And here u is equal to u, just like that. Really, u is equal to natural log of x, but we'll worry about that at the end. So here that's going to equal to, and now we're just using this formula here. It's going to be negative 2 times 2 times a minus b, which is 3, times u over 3 times our b, which is also the number 3, squared, times the square root of a, which is the number 2, plus b, which is the number 3, times u, plus our constant of integration. Okay. So all I'm doing is I'm using this formula here I'm using this formula here and just substituting in the appropriate values. I know my A, I know my B, I'm going to leave U as U for now, and I have that result. So now what I can do is I can simplify. I can take this expression and say, okay, well, let's write these out as simply as they'll go. That's going to be 2 times 2 is 4, times negative 2 is negative 8. 3 times u, that's a negative, times a negative 2, that's a positive 6u, over 3 squared is 9, times 3 is 27. So that's going to be 6u minus 8 over 27, times the square root of 2 plus 3u plus our constant of integration. Note that the bulk of the work here was not doing the integration. The integration was done for us on the table. The bulk of the work here is pattern recognition, going through and trying different values for your substitution of u. Once you find a correct one, and notice the language there, a correct one, there may be more than one. Once you find a correct one, the substitution yields you something on your table, and after that it's just a matter of substitution and some light arithmetic and algebra. Finally, u is the natural log of a, so that's the natural log of x. So that's going to be 6 natural log of x minus 8 over 27 times the square root of 2 plus 3 natural log of x plus our constant of integration. And all that came from just recognizing that formula number 21 here was the correct one to use. All right, let's take a look at one more example. Same kind of problem. We're going to look for a substitution and then search for that substitution on our table. So let's look at finding the integral of the cotangent to the 5th power of the square root of x over the square root of x dx. You might try this if you have your book available right now, or if it's something that you can easily look up. You might try this and see if you can find a substitution. Remember that the integration tables that I'm currently looking at are in the back of your book in the appendix section, Appendix B, and it'll be it'll look like that. Integration tables, Appendix B. If you go ahead and pause the video, give that a try, and once you're done, go ahead and unpause and we can go through that one together. For anyone who wished to try it and just didn't have a book available, or at least not around you right now, you can, let me narrow it down a bit for you. That was, where was that? Right here. So it's going to be an integral that's on this page here. So if you wanted to try it but just didn't have a book easily available right now, you can try it now. Go ahead and pause the video and give that a try. All right, so let's go through the problem here. Here, again, it's unlikely we'll find something that looks exactly like this, but with a substitution we'll find something that looks similar enough. Right off the bat, I recognize, hey, the square root of x has a derivative that's 1 over 2 root x. So right there, that's probably going to yield a substitution that works nicely. Again, there's no guarantees on any of these things, but just from results that I remember from Cal 1 and some stuff that we've seen in Chapter 5 here, whenever you take the derivative of the square root of x, you end up with 1 over 2 root x. So having a root x in the denominator means that that's the derivative of this expression here. So no guarantees, but it's worth a try. U is equal to the square root of x, so the derivative of the square root of x would be 1 over 2 root x, And so the differential, du, is 1 over 2 root x dx, which, yeah, sure enough, that's almost exactly what I have, 1 over root x dx. I just need to double both sides to make it exactly correct. 2 du is 1 over root x dx. So here I can write this as the integral of the cotangent to the 5th power of u, and then that's 1 over square root of x dx. That's your 2 du. So I'll kick the 2 to the outside, and that's du there. Okay. So now, looking at our table, we find here we have this formula for the integral of the cotangent to a power of u du, which is what we have now. Notice that this is not a full result. Rather, it's what I've referred to a couple of times already as a reduction formula. In previous sections, we've called reduction formulas anything where instead of giving you an answer, it gives you an integral in terms of another integral. Or in other words, here, you don't get an answer. You're told, hey, you can trade in this integral for a slightly simpler integral. So let's go ahead and use that one. All right, so let's see if I can't put these together. Let's see, I think we should be able to see that now. There we go. So the cotangent to a power of u du is equal to negative the cotangent of the original power minus 1 of u over n minus 1 minus this new integral, which is the same as the previous integral, but with a power 2 less than before. So that's going to look like this. We're going to leave our 2 there because that's just a constant. And then that's going to be multiplied by negative the cotangent of, if our original power is 5, this is going to have power 5 minus 1. In fact, let me even write it that way. I'll simplify here in a moment. 5 minus 1 of u over that same denominator. That same power will be our denominator, so 5 minus 1 minus the integral of, this is now the cotangent, and now this power is going to be the original power n, which is 5, but now minus 2. Du. And note that here they, du, and note here that they give us a restriction. They say if n is equal to 1, this is not valid. Well, what do we do if n is equal to 1? Well, then we just take the integral of the cotangent. We know that one. That's negative the natural log of the sum of the cotangent and the cosecant. All right, that's something we saw in Cal 1. So this is meant for higher powers. If the power is 1, you already know how to do that one. We're not going to worry about a plus c just yet because we haven't actually resolved this. We're still just changing one integral for another. But we can simplify. Let's see here. That's going to be negative 2. I'm just distributing my 2 here. Negative 2 cotangent to the power 4 of u over 4. I can reduce that even. So 2 over 4, I can write that as 1 over 2. Okay. Minus double. I'm just distributing my 2 here. The integral of the cotangent to the third of u du. But notice that now I can use my reduction formula, in fact the exact same reduction formula again. So let me just take this right here and resolve just this part using a reduction formula. Here I'm just going to rewrite that stuff. That's negative cotangent to the fourth of u over 2 minus double, and I'm using a reduction formula on this. Okay, well that's going to be negative the cotangent of, take your power, minus 1, 3 minus 1 of u, over that power is your denominator, right over here. So that's 3 minus 1 minus the integral of cotangent of, and you're going to take your power that you had before and subtract 2 from it. Okay, well I started with a power of 3, so that's going to be 3 minus 2 of u du. So now we can simplify some stuff. At this point, we are done using that reduction formula. It looks like we're down to a power 1 now, which is something we can do without the reduction formula. So let's simplify some stuff here. That's negative the cotangent to the fourth of u over 2. Let me distribute that negative 2 there. So double negative makes that a plus. So that'll be plus double the cotangent to the power of 3 minus 1, that's power 2 of u over 2. Double negative makes that a plus 2 times the integral of the cotangent to the power 1, which I'm not even going to write, power 1, cotangent of u du. Looks like that. And that's an integral we know how to do. That's, oh, I'm sorry. A moment ago I said the natural log of the absolute value of the sum of cosecant and cotangent. I was thinking of the integral of the secant function. The cosecant function. The integral of the cotangent function, you can just think of cotangent as being cosine over sine of u, and then use a u substitution. So here we actually could handle this using a substitution. We'll just write that as cosine of u over sine of u, and then the numerator is the derivative of the denominator. But since we are using tables in this section, it may actually be in our interest to just look for that up on a table. So going back to our table, you'll note that that's actually one that just appears as is. Here, the integral of the cotangent of u du is the natural log of the absolute value of the sine of u, which is what you would have gotten if you used your substitution. If you had written this as cosine of u over sine of u, you end up with a substitution that looks like dw over w, which is the natural log of the denominator, or in other words, the natural log of the sine of u. So here, we just pop that in. The integral of the cotangent of u du is the natural log of the absolute value of the sine of u, plus our constant of integration. So that's negative cotangent to the fourth of u over 2, plus 2 cotangent squared of u also over 2, plus 2 times the natural log of the absolute value of the sine of u, plus a constant of integration. Here, these 2's divide away. You have a 2 in your numerator and a 2 in your denominator, here and here. And finally, don't forget, don't leave it like this. The original function was in terms of x. So here, u is the square root of x. So this can be back substituted to give us negative the cotangent to the fourth of the square root of x over 2, plus cotangent squared of the square root of x, those 2's are gone, plus double the natural log of the absolute value of the sine of the square root of x, plus some constant of integration. And there we go. Note that integration by tables does not invalidate our previous methods. Rather, it highlights another reason why they're important. Note that very few, if any, of our integrals that we ever do are directly on this table. Rather, we have to manipulate the integrands to make them fit this form. And how do we manipulate them? Well, we manipulate them using u substitutions, by using the chain rule, by separating things out using partial fractions and making sure that our expressions are, when we integrate those pieces of the partial fraction, those pieces will appear on this table, or by performing trigonometric substitutions and ending up with results that are on this table. This integration by tables does not make using our techniques from previous sections obsolete. Rather, it gives you another reason why you want those. The integrals don't fit this table on their own. You have to simplify them, you have to rewrite them, or you have to manipulate them using integration by parts, partial fractions, trig substitutions, u substitutions, the chain rule, and other algebraic manipulations to get you to the point where you can use the table. So using the previous techniques that we've learned in tandem with this table is what they're intended for. The tables, I mean, is what the tables are intended for, to be used in tandem with our previous techniques. And that's it. This section is rather short because, again, there's not really any new techniques to cover. Rather, it's highlighting the importance of things like substitution and rewriting expressions, the importance of using reduction formulas as we've seen in previous sections, but now in the context of these tables, which really are a memory-saving device. I know how to use the techniques. I don't actually have to memorize 100 different formulas. I can memorize a few basic formulas and make sure I understand my techniques very, very well, my substitution techniques and my basic integration techniques. Once I have those, other things I can look up. So that is it for this section. If anybody has any questions, comments, or problems, please let me know. Note that the assignment for this section is about the same length as the other sections. However, as a bit of warning, some students do find the assignments from this section slightly frustrating, even in the context of this chapter, because there are different formulas you can use, which means that someone might have simplified something to look like this, and someone else might have used a completely different substitution method and ended up with something that looks like this, and they might both be valid. So if you are checking your answers in the answer key in the back of the book, you might note that you have an answer that is radically different from what you might see on your work, but that doesn't mean it's wrong. As long as the substitutions are valid and as long as the formula you're using is matching the integral that you're looking for, it is still correct, even if yours looks a little or very different than what you might see in the answer guides. So if anybody has any questions, comments, or problems, please let me know. Go ahead and reach out to me, make a note of your questions, and let me know during office hours or during our next meeting. And I hope everyone has a nice day.